Hey guys, I'm here back with another math video. Today we're going to be tackling an OMO problem. It's pretty hard, so don't be sad if you can't solve it. Just take a look at it and try to solve it. Oh, by the way, it's not supposed to be 2n plus 1. This is, whoops. This is, n plus 1. Okay, now time for the solution. So, it's a sequence problem, and I really hate sequencing problems. But, nonetheless, let's try to find the pattern. After all, sequence problem, you have to find the pattern. So we'll start with this sequence, because this looks rather interesting. Equals x squared xn plus 1 squared minus 1 over xn. And maybe we can do something. Maybe let's try to just manipulate it a bit, you know? After all, this doesn't look too helpful right here. I mean, we could factor the top, but if you did that, you'll see it doesn't actually get you anywhere. Again, just try to look for the patterns. Okay, so we have this, and let's just move the 1 to the other side. You know, maybe you guys can try to look at. So what's interesting about this equation? So does it look interesting at all? Actually, this sort of reminds me of Ptolemy's theorem. And Ptolemy's theorem basically says that if you have a circle with a cyclic quadrilateral inside A, B, C, D, then AB times CD plus BC times AD equals AC times BD. Basically, what this says is that the sum of the products of opposite sides, AB times CD plus BC times AD, this sum is equal to the product of the diagonals. And, well, let's try to see how this equation relates to this. So, we see like there's one thing multiplied by one thing on one side plus another term plus this squared. So I think what we can do, we can basically state that if AB was xn plus 1 and CD was x2, then it would, oh sorry, xn, wait, where did x2 even come from? It's xn. Then the quadrilateral would look like this. So this AB would be x, and this would be x and plus 2. Wow, I wrote this equation out wrong. And these are the diagonals. And what would the sides be? Well, the sides have to multiply to 1, right? AD times BC, or here, have to multiply to 1. And what multiplies to... And we know the diagonals have to be equal to the same, because the diagonals are going to be x n plus 1. So the diagonals are the same, and the top and bottom are just these. And the sides, if you sort of look at it, I don't want to prove it right now, but they also sort of have to be the same. You can just look at it, symmetry, diagonals are the same, sides also have to be the same. And what times what equals 1, and that's just 1. So, and don't forget, it's cyclic. It has to be cyclic. So this is what we have right now. And, well, looks like we're getting somewhere, sort of, but sort of like, you know, sort of like, it's probably just luck, probably coincidence. So let's try this with x1 equals 1. Let's just try that. So if x1 equals 1, so x1 equals 1, so that would be 1, 1, 1, x3, x2 would be here. Alright, and let's try it with x2, I guess. So this would be x2, 1, 1, x3, and then x4. How do we make it so that this sort of goes into this? I mean, like, we have these two separate figures. Maybe we can combine them into one. And actually, you can do this. So 1, 1. This would x2. And then we don't have to draw the other diagonal, because when you have x2 and then 1 here, you can do this. 1, x3. Don't forget, this base is x3. because we have this triangle. And then the top is x2, the diagonals are x3, so this is x4. And we can do it again, actually. I mean, we can do it again. So this this diagonal is x4, and then I should probably draw this, and sort of bad. But if this diagonal is x4, then we can actually keep go. I can't do it on this drawing because it's a rather bad drawing. But okay, now we know this. We can actually perpetuate the sequence in geometry, which I know is hard. It's hard for you, it's hard to understand right now. But maybe if I draw it out better, you'll see what I mean. So remember, all these have to be cyclic. All these quadrilaterals have to be cyclic. So let's draw a giant circle. All right. There's one. It's really thin for now. And then of course, okay, so this is 1, 1, 1, x2, x3. Now let's draw the second one in the sequence. So now we can do this, as we said before. And it's hard to see, but this is actually x4. And why is that? If this is 1, we have another quadrilateral here. So this quadrilateral right here is 1, 1, 1, x2 as the diagonal, x3 as the base. And this quadrilateral, this actually has x2 as the top, 1, 1, x3 as the diagonal, and x4 as the base. So it actually satisfies the equation that we had. It actually satisfies the equation because again, so if this diagonal is x3, this diagonal is also x3. And x3 times x3 is x3 squared equals 1, which is the product of these two sides, plus x2 times x4, and that satisfies this equation right here. And this is satisfied in geometry, which I think is really cool. So let's just keep going. Let's keep going. So this is 1. This is x5. Diagonal is x4, and of course you can draw this. This diagonal is also x3 because the diagonals are the same. And the top is x3. The diagonal is x4 and the bottom is x5. So what if we keep doing this? x6, oh frick, whoops. x7, x8, x9, and you can see where we're going with this, right? x10, x11. I didn't draw the diagram very well there, but we stop here because you know why? x12 is 0. And so far, so if this is x5, x6, x7, x8, x9, x10, x11. So far, all of these lengths is just the length of this point. It's just the length of this point to here, to one of the lengths on to one point on the circle here, and they're all 1. So if this is x10 and x11 and x12 is 0, we know that the rest of this thing, because I didn't draw it very well, this thing is 1, and x12 is the same point as this. Since x12 equals 0, this point right here has to be x12. Since x11, x10, x9 are all determined by the length of this point to a certain point in the circle, if the length is 0, x12 has to be this point. And this has to equal 1. This right here. So that's the case. What do we have here? I'll tell you what we have here. We have a perfect, let's see, how many sides are there? 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. We have a perfect 12-sided figure with everything, all the lengths equal to 1. So it's a perfect polygon. So we need to find, of course, that question asks the value of x2. And x2, we go all the way back to the beginning. And x2 is just this little sliver right here. Alright. And what is x2 exactly? Well, this is x2. This is 1. This is 1. And, of course, since this is a 12-sided figure, you can find the angle of this, which is 150, 15, 15. And to find x2, this is x2 over 2, x2 over 2. So x2 over 2 divided by 1 equals cosine of 15. So x2 equals 2 cosine 15. And you can simplify that to, I think it's square root 6 plus, wait a second, oh yeah, square root 6 plus square root 2 over 2. And that's the answer. It's a very cool problem, I think, because you never think you actually get like geometry out of a sequence problem, right? But that's how it works. I think it's pretty cool. So I hope you found this problem interesting, and we'll see you next week. 1 equals 15 times dE over 8. So you get dE equals 49 over 8. And then you get that this thing is 8. If you add 15 over 8 plus 49 over 8 together, that's 64. So that entire line AE is 8. And so we have all these lengths. What next? Now is time for the really annoying part. Now is time for some it's where you deal with angles, basically. Alright, now don't worry, there's no trigonometry. There is